in case if I'm not audible, feel free to let me know. Those who are in the Zoom. This was a paper which was released in like a month back by this group, by Google and UCL. So they want to find a new optimization algorithm. So they come up with a nice evolutionary method so that they can find a new optimization method. It's called Lion, and then they compare how it performs compared to another optimizers. So in the the Twitter community, people have tried this optimizer, so it's called Lion, and like as initial impressions, it needs just 30% less memory to keep the gradients and stuff, and also the convergence seems a bit faster. However, some people have had some trouble getting it to work, and then it has worked, and so people are trying out this optimizer and seeing whether it can replace Adam or not. Yeah, so I'll give a brief intro about what this optimizer is, and then we'll go into how this is found by an evolutionary algorithm. So this optimizer is not something a person came up with a pseudocode or something. It's something an evolutionary process actually found. So before going on to the evolutionary process, I'll just summarize some stuff about this method. So we know that from the LM optimizer, we have a notion called moments, momentum, and something called adaptive gradients. So basically, we keep the first and second moments of the gradients, is mk and vk, and we use that to have that momentum and scaling of the learning rate so that it actually has adaptive learning rates to all the dimensions. So in summary, that's what adapt does. Compared to that, this method keeps only the momentum, and as I mentioned, rather than adaptive learning rates for all the dimensions, this method has uniform magnitudes. So this seems somewhat unintuitive compared to like in the 2016-2015 people came up with this adaptive method so that we can have different learning rates for different parameters. But in essence, it seems a bit unintuitive, but let's get into like how can this be helpful. So this is sort of the pseudocode for this line optimizer. We'll discuss this later as well. I'll just give the pseudocode here. So as we mentioned, it just has the momentum term, which is the first moment of the gradients, and it sends through this signum function and just clips it before applying the updates. So that's like the essence of it. We'll get to the details of this optimizer later, but first let's see how we can search for an optimizer in the first place. So we'll look at how this searching process is done, and then we'll get into what the optimizer characteristics are. So as we talked earlier, the de facto standard optimizers are Adam and Ada factor. I have not used this much, but I think the concepts are mostly similar. So when searching for optimizers, there are a couple of ways to do this. So there's this one approach where we train a neural network to output the updates. So it's sort of a black box method. Because of that, there's like generalizability issues, and typically these learning to optimize methods are trained on a small number of tasks. So there's a bit of generalizability issues in this line of work. Then there's another direction where they use reinforcement learning or sampling methods, where the search space is defined by trees. So, so what they say is, to limit this search space, we have to make some tough choices where we fix some operands. So, such as momentum and gradient, those notions we have to fix them. So, there's less potential for new discovery. However, WadduwageLab 0, which was proposed in 2020, has been a very good effort in tackling searching for new programs. So if we briefly look at what WadduwageLab is, so they want to discover an algorithm by basic mathematical operations. So if they have basic statements in as in a pseudocode, they want to come up with the most a better method of arranging these mathematical operations to get a working solution. So this paper, I haven't gone much deep into it, but what they say is through evolution research, they can discover a two-line neural network trained by backpropagation. So this paper, the paper we are discussing today uses concepts from the WadduwageLab paper and actually focuses just on the optimization part, finding a new optimizer. So now I'll get into the details how this can be done. So first thing is we need to formulate this algorithm as a symbolic manner. So rather than a numerical like a black box solution, we need to come up with some sort of an equation or computer program so that it's easy to analyze and that algorithm can be easily applied to a new task. Also, the program length naturally gives us an intuition on how complex the algorithm is. So in this paper, the goal is to come up with a symbolic formulation and try to optimize it. So towards that goal, we have some things to clear up. So the first thing is, what is the program space? And since I call this as an evolutionary process, so we have, maybe you have heard about genetic algorithms where there's this crossover and mutations. So for these programs also we need to come up with some sort of mutation. So we need to look into those as well. And let's see, since we are dealing with a lot of a large search space, how we can efficiently search. So in terms of the program search space, what the authors mention is we need to be flexible in terms of the search space so that we can discover new stuff. The other one is the program should be easy to apply to new, incorporate with the existing machine learning workflow. The other one is rather than the very low-level details, we need to come up with a program that deals with much higher level design. So these are some design choices that they talk about. So now let's exactly look at what this means. So, all right. So this function is called the train function, and we have the model weights and the gradient with respect to parameters and the learning rate coming in as inputs. So these three are coming in as inputs, and then our goal is to update the new set of weights that should be the new set of weights that's trained through this function. So we have some flexibility in terms of capturing historical info. That means like a buffer, we have the flexibility to keep variables so that we can store some historical parameters. So this program 3 is like the overall pseudocode through which we are going to learn a new optimizer. So, even though this makes somewhat sense to us, let's, in abstract way, let's just think this is a function which takes the weights, gradient, learning rate, and returns what update we need to do. And all these lines are just some functions which can take a constant or existing variable and return new variable. So they say that there's no restriction of number of statements or the local variables. And in terms of these functions, they have 45 commonly used functions in NumPy or JAX or like in linear algebra. So those functions are like listed here, like binary functions, the linear algebraic things that we need, dot product, etc. So those are the available functions through which we can formulate this train function. So we can think of it as just sequence of steps which does some mathematical operations on constants and existing variables. So, alright, so now we have some sense on the program space. Now let's discuss about what sort of mutations are possible in this program. So the authors talk about, yeah, as we know, like genetic algorithms. So the gradient-based algorithms, we have a signal on how to navigate in the loss landscape. However, in the genetic or evolutionary methods, we always rely on mutations in order to discover new stuff. So through mutations, we see whether that new child performs well, and then we decide how we can carry on in the population. So without mutations, we can't do anything. So in terms of mutations, in this train function, we can add a new statement at a random location with arbitrary chosen, since we have this pool of 45 functions and arguments, we can insert a new statement. So that's one thing. And the other is we can delete a randomly chosen statement. The third is modifying a random statement. That is by altering the arguments of the function. So, so as we discussed, the arguments can be a constant or a variable existing in the program. So when we talk about altering the function arguments, we can either replace with an existing variable or we can generate a new constant. So they mentioned that they sample from normal distribution, or they can mutate the constant by a factor. So by this 2 to the power a factor, they can mutate the existing constant. So now in terms of the training program, these are the available mutations that we can do to come up with a better, potentially better algorithm. Yeah. So however, if we look at the search space, the authors come up with a I think an upper bound or an approximate for the rough estimate on the number of programs. So it seems that like intuitively also it makes sense. Let's say we have 45 mathematical functions and we have numerous choices for the constants. So definitely most of the programs that we can construct from these functions will not make sense. So like doing a random search on this space wouldn't actually give us meaningful solutions for this train function because it's infinitely large on how we can manipulate these variables to return something. So they do an experiment to check this as well. We'll get to that. I mean, just randomly playing around with these functions and seeing whether there's a nice solution. But they do a random search and also show that it doesn't like give a good result. Alright, so now we have an intuition on the number of, the mutations and also the search space. Now we come to the exact searching technique that they use. So what they use is something called evolution, regularized evolution. So this regularized evolution method is something that's been applied in the WadduwageLab paper as well, if I recall correctly, WadduwageLab 0 paper. So if we go to this regularized evolution, it's also called aging evolution. What happens is we have initially a population of algorithms. So these are some example, train functions. In the first step, so the population we can define, we fix that number. So in the first step, what we do is we remove the oldest algorithm that exists in the population. So after removing this one out of the 5, we are left with 4 algorithms. Then we do something called tournament selection, where that constant is also arbitrary. Like if we take t equals 3, what we do is in the next step, we randomly select 3 algorithms and see which one performs the best. So we had 5, we eliminated the oldest, we took the remaining 4. Based on this tournament selection T, we randomly pick some algorithms and we select the best one. After selecting the best one, what we do is we copy that algorithm, then we do this mutation. So we had a copy of the best algorithm and we mutate, and we add it to the population. So now also we are left with let's say 5 algorithms. So we repeatedly do this step. So this is like the overall regularized evolution concept. And in terms of this paper, what they mentioned is if we start with a random population, uh, it, it doesn't help us much in the convergence process, because this is like an infinite space of mathematical operations. Starting randomly is not a good way. So they sort of bias this process. It's called bomb start. So the initial population is basically the random optimizer. So in terms of these P and T parameters, they have a population size of 1000 and the tournament selection size is 2, which basically means that we randomly select 2 and see what performs best and then mutate.
So all of the initial population is same.
Sorry.
So you said the initial population is at a W. Is it like how the population different, or are they the same copies of the same thing?
If I recall correctly, it's the same thing. But I need to actually double check. I'll need to actually double check. They mentioned that they initialized by the nice.
Yeah, that's okay. Learn us more later.
Yeah, that's actually very important design principles. Yeah, I'll check, get back to that. And also with this bomb start, but they use something called pre-start. So pre-starts, so there are like 2 approaches we can take. So the first one is we just restart again, keeping faith in randomness. So there's no any random seed fixed or anything. So this sort of restart we can do in parallel because it's just running on like 2 different times. So this first approach, they can like run different initializations in different seeds in parallel. And the second type of restart is restarting to the best algorithm found. So I think what they do is after 300k steps, they select the best algorithm and initialize the population and start from there. So that's this second one. Yeah. So if you look at the results, so this red dashed line represents the random search. So that's basically just doing random exploration without any mutation or anything. So they actually run these to get these 2 baselines. After, I mean, they give 4 times more compute power to get these baselines. I think that's to have fair comparison. Alright, so in this green one, they only allow the constant to mutate in the population rather than adding new statements on anything. It's just the constants that mutate. Alright, so this blue color curve represents like the mean and the standard error of 5 experiments which ran, and after 300k steps of progress, they restart with the best algorithm found. So that's actually to improve the fitness further.
So how do they measure fitness?
I think that's a value based on the proxy task. So they actually have 2 tasks, like a visual task and a language modeling task. In the vision task, they had a vision transformer. Yeah, so that they actually measure the performance on those 2. I'm not exactly sure how both of those results are combined to get the fitness. Yeah. So this is like the overall training occur. So even though this seems nice, there's
So
like
one more thing. So this experiment, if I understood it right, so for every point in the search progress, they have the optimizer and then they train these two models until they converge and then report one number, right?
oh yes,
So it's a very large experiment.
yes, that's true. Like as you mentioned, let's say from the start we have 1,000 optimizers. So 1,000 optimizers, and then we eliminate the oldest one. Then we actually through 12 selection, they pick two random ones. So I think because that t equals 2, it's not that we train all the ones. We randomly take 2, and then we train models, and then we select the best one. Then we make a copy of the best one, and then mutate. So I think because of this t equals 2, it's sort of tractable. I mean, in terms of one step, we are just training two optimizers and selecting who is the best. Even so, like I think running for 300,000 steps means training, like at each step we train two models. So yeah, that's a very important question.
Yeah, I didn't even notice the cake. It's 300,000.
Yeah, however, like, as this is like a very, yeah, as this seems very inefficient, they come up with very nice nice step, which they call proving through abstract execution. So what they say is that when we do these sort of mutations, we always come up with programs which are sort of invalid or which has type or shape errors. And sometimes these programs already have been, I mean, explored previously. So those are functionally equivalent programs, and there are redundant statements. So there could be optimizers with these issues. So they come up with this step called abstract execution, where it takes a very fractional amount of time to actually evaluate whether it has some errors like these. And also they say that they compute a unique hash which like which fingerprints how the inputs are connected to the output. I mean how that computation looks like, so that we can efficiently cache. Yeah, that's one thing. And also it can identify redundant statements. So I think this abstract execution, they have discussed about this in that supplementary as well. So I think this helps a lot to uh, quickly invalidate like invalid solutions or solutions we have already found. So yeah, so they say that this has negligible cost compared to the actual training process, which makes sense. Yeah, we'll also get back to this in a bit as well. So this program 8 in the left, this is like the actual optimizer that they have found. And so I think since, I mean, without any human intervention, since this all mutations and stuff, it looks very messy, but they actually clean it up to, I think there might be redundant or statements which are not used, so they clean it up and present the algorithm line. Uh, if we talk a bit about these redundant statements, so as we progress in the search space, uh, yeah, so this blue line indicates the fitness. So this cache hit rate means, so at the end of all the steps, it seems like we have mostly encountered like 89%, which are already existing in the cache. So yeah, so also in the redundant statement wise, it's also like 69%. They have found programs which has redundant statements. So they mentioned that this abstract execution is very important in terms of like quickly getting the output. So yeah, so they mentioned that if we have, when we come up with a new child, if we have already uh, uh, if we have already encountered a child before, it will be a waste of resources to run that again. So overall, they mentioned that um, even though like 200K to 300K programs are generated, they mentioned that because of caching, we will actually evaluate roughly 20 to 30K models. So it's something I think we need to look at more in terms of abstract execution. But I think like as an elegant point of this evolution research method, this caching is something like uh, very nice about this algorithm. Uh, yeah. So in terms of the proxy task, they actually train with small models. Uh, yeah, like I think yeah, transformers with three or two layers. So as the proxy task to evaluate how well these optimizers are, they sort of constrain that. Um, so evaluation of proxy task takes around 20 minutes, like a TPU chip. Right. So after this process, there are a couple of more steps done to select methods that generalize well. I haven't like included that in my presentation, but there's like more steps to filter out the best performing ones in generalize. But overall, um, if we now transition towards the actual optimizer method, so this evolution process has like um, discovered existing and this new line optimizer. So the existing ones are like anagram, those sort of algorithms. Um, yeah, so as we discussed earlier, now let's get into the line optimizer. So after cleaning this optimizer and writing it as a pseudocode, um, what we essentially have is, so we uh, have this empty in the sense we have the first moments of the gradient, like, and then we do have it. However, before like multiplying it with the learning rate, we send it to the signal function, which essentially flips it to +1 or -1. So, like, this seems like a very noisy process of clipping. Let's say 0. Let's say we had a CT value of 0.8, we just clip it to 1. I mean, so that seems like a very noisy process. However, like if we uh, discuss why this might work. So what they say is this signal function acts as a regularization. So yeah, so what they have observed is since this adds noise to the updates, this helps with generalization. We'll get to that in a bit in terms of experiments.
Can you go back to the previous slide?
Sure.
So what's exactly the what is clipped exactly?
Yeah, CT is actually it's like a linear combination of the past first moment and the current gradient. So, yeah, so this is the current gradient, and uh, so in the atom optimizer, so this structure looks a bit different if I will compare them side by side. So in the atom optimizer, what we have is in terms of the first movement, we like have a linear combination of the pre. I mean, this is like a exponential moving average of the first order gradients. So when we have this empty value, we directly, I mean, after this bias correction, which is a, we can like disregard in terms of that. So just gets it here. But here in terms of like the step execution process, yeah, what they do is they initially have this linear combination of the past gradients and the current one, and then they send to a signal function. Then they update the moving average through a separate beta constant. So even though this has just the momentum, it has two constants, two hyperparameters, beta 1 and beta 2. They can keep.
Okay, so the new thing that the search found is to actually mess with the momentum.
Yes. Yeah. Okay, yeah. The signal function is the main thing I think it discovered, and getting rid of the adaptive part where in the Adam optimizer we have this second order gradients which we sum it up and we scale sort of a scaling of the learning rate. If we take this part, like this is divided by that exponential moving average of the second order gradients. But here, that sort of scaling for each dimension is not there. So one of the things, like adaptive gradient methods authors in 2016 discussed was if we have that scaling, if we take a CNN, it helps different parts of the CNN to learn in a different manner. However, this seems like very unintuitive in terms of that, like getting rid of that part. Yeah. In terms of this signal function, what they have seen is that, in terms of other properties, it has less number of hyperparameters because we don't have that second order. Yeah, I need to actually double check this. So this also has beta 1 and beta 2. But I think there might be this tunable hyperparameters. So the event wise update is like binary 1 and 0. So because of this noisy set, they have discovered that this has higher training error compared to Adam. So this is like a image classification. Yeah. So the training loss is higher for Lion actually. However, in terms of validation, if you look at it, it has like 2% increase. So it has helped in terms of generalization. I think that's like a takeaway. And in terms of memory, since we can just, so this B float 16, if we keep it in this sort of variable, I think there's like a lot of memory reduction. I think overall they mentioned around 30% less memory requirement. So I think that's the main benefit, having the comparable accuracy of Adam, having this memory benefit. And also they have compared with existing popular optimizers, which are very well used. So what they say is, Lion is outperforming these, but it's like minor like improvement. However, overall, in terms of having a simple algorithm, it's actually better in terms of memory, and I think execution speed is also getting faster. There are a couple of things we need to discuss where this line optimizer needs to have. If we consider small batch sizes, the improvement is not much evident. So what they say is this algorithm prefers larger batch sizes. Um, yeah, in terms of execution. Yeah, and also from what I've seen in the existing community was that it helps us to get the performance which with very much low number of steps. That's the sort of thing there. So I think this curve also highlights that. So in terms of using linear experiments, they say that because of this signal function clipping, we need to mean, overall, these updates become much larger. So we need to actually have sort of a 10 times smaller learning rate. And if we have strong augmentations already in place, the improvement of lion might be a bit smaller. So those are like some intuitions that we can take. Yeah, so in terms of this overall searching process, the authors say that since they initialize with the LM as the population, we are sort of already biased towards that. Yeah, in the search process. So it's sort of a future thing that they can look at. And also, as we discussed, if there's strong augmentations, they don't see a lot of improvement. Yeah. So overall, I think in terms of this paper, I think how they do this evolutionary process is very nice with some nice steps like caching and abstract execution. And yeah, and it shows that if a human came up with sort of like a human choice would have tried this sort of signal function which is unintuitive. So yeah, it reminded me of like optical I mean, this evolution process has discovered something which goes against our intuitions, but it performs well. So yeah, I also tried this optimized. I mean, on optical classification, one-stop application.
How did it work with the quantization?
Yep.
I don't think it does much. I think maybe it is robust too.
So these are the two experiments I have compared. So the one on the right uses the LM optimized learning rate of 0.01. Yeah, so these uses are multi-level sigmoid quantization method. So this is like the new configurations of, I mean, the fabrication team gave us like last week. So the like dark green one is on this line optimized with much 10 times low learning rate. In terms of, at least from this experiment, it seems like it has been more performance.
It does. Which one is the line?
Yeah, one on the top. I mean, like 1% improvement sort of.
Is it the line?
Yeah. So that was my initial experiment.
But is it like running? So step means the box are
Box. Yeah. This is the
is
validation.
it running or
It's still running. Yeah.
and do you see the training? There less training error.
I actually did not see. Yeah, I did not see. It actually had a higher training loss. Bit higher as of now.
It has higher training cost, and so it reduces the. It's not they say. They say it has higher training cost, but okay, so.
Yeah, so I think that was what I had prepared for the presentation. I think overall, like this evolution process, I think then I can get some more intuitions on like that process as well. How they do some, how can they do like faster searching process.
Yeah, but I think like it's different, right? What they are doing is like more advanced than what they are doing. What they are doing is actually looking for searching optimizer space, right? They are
Oh,
have
yes.
the design and optimizer using evolution to.
Yeah.
Yeah, but we are using evolution as an optimizer.
Yes. Yeah, in terms of problem, those are very. I think that caching stuff, maybe. Not sure. Like,
So the caching is also different, right? Because the caching is just evaluating the optimizer they found.
the functional functionality of the optimizer is cached. Yes.
It is more similar to like this neural architecture search than this neural optimizer search, right? But what is interesting is I've seen like some work like coming up. It is more similar to like all optical or like the optical architecture search in terms of what we are doing. There are people, I think there's something now, some people using machine learning to actually design stuff in a sense. So this is using design programs, right? Right. But the takeaway is probably like using evolutionary algorithms to optimize designs, right? Which are like not differentiable.
And if we can have nice playground where we can quickly do that mutation instead. Initially, they had, so in terms of these design choices for the program, so currently they have 45 only, things they can try out. Initially, they had also had these loops and sort of things as well, conditional statements. They have found that that doesn't bring much value, so they have got rid of that.
Ravit, can you hear me right? Hello.
Yeah.
Yes.
I just I was like thinking about like the generalization aspect because like as you mentioned so it seems like we kind of train like we find the optimizer for a per data for a particular task because like so the initial kind of intuition I got is like we kind of we are finding the optimizer which is like specifically working better for a given loss landscape kind of a way because we have the proxy task, right? So we find the optimizer which works best on that particular loss landscapes kind of. So so do you have like any comments on like how like it why it kind of performs like generalized well on like other kind of loss landscapes as example like if you consider Adam it is like a algorithm which is like it develops by intuitions, right? It is just like kind of like researchers like develop it by like using some logical some like things, but so here like it is kind of the task defines what optimizer should be. Yeah.
So the what you mean is like since they have just two proxy tasks on which they evaluate the
Yeah.
fitness, how it can be generalized. Yeah.
So yeah, what I was thinking is like why it not be like similar to like just training like finding the so what I was thinking is like why it not be like similar to finding the best architecture that performs on that task because we are finding like algorithm which makes the model best at the given tasks, right? So it is kind of like so at the end what we do is like trying to get high accuracy on particular like two tasks because like the proxy tasks. Did you like get my point? So yeah. So if I like explain again, like so initially what I understood is like we have proxy tasks. So like we try to come up with the optimizer which makes like a model better on those proxy tasks, right? So I was thinking like how why it should be generalized on like other tasks as well because we only like optimize the optimizer for that given tasks. Yeah, I just what do you have any thoughts on that?
I think actually this is a problem that the authors have encountered. I actually skipped this generalization section altogether. So they say that when they, as you mentioned, when they train for this proxy task, so go to figure 3. they have actually seen this like overfitting to the proxy task as well. I think it's in the supplementary. However, what they, I actually didn't dive much into this section. So what they say is they actually see this generalization gap from the proxy task to the target task. So to sort of select out once generalized, they run on like much higher task as well. So I think that requires days of running. These target tasks are like 10 to the 4 times larger as they mentioned here. I need to actually go through this section a bit on how exactly they mitigate this generalization gap. Yeah.
Okay, yeah. Okay, thank you.
They say that they sort of correct promising programs, but I didn't actually get this part correctly. So,
Okay,
as you
they
mentioned,
might
it's
like
like
consider like they might consider like tasks with like different complexities. Maybe I am not sure. Yeah, that might be as proxy tasks.
oh
Yeah,
yes.
yeah. Thank you. Yeah.